Hello friends, good morning to all. Welcome back to the IARE YouTube channel. Today, in this presentation, I am going to discuss about of the scheduling algorithms, which are, in this, we will discuss first come, first serve scheduling algorithm. So in this presentation, today I am going to discuss what do you mean by CPU scheduling and the scheduling algorithms. In the scheduling algorithms, the first algorithm, first come, first serve scheduling algorithm is going to discuss in today's session. After the end of the session, so the student able to understand role of the scheduler and how that behavior influence the performance of the system, and also he can know the difference between the IPO bound process and CPU bound process and how they are related to the scheduling. These are the outcomes the students able to carry out of this session. So let us see the first, what do you mean by CPU scheduling? So in earlier session, we have already discussed about the what do you mean by scheduling, what is the importance of scheduling, and what are the different kinds of the schedulers and different kinds of the scheduling queues and the scheduling criteria, what parameters influence the scheduling algorithms. So these topics already discussed in the previous session. If anyone is missing, please go back to the previous session and gain the knowledge about of that. So in this presentation, we are going to see the scheduling algorithms. So before that, so we are going to see that the CPU scheduling. Another word is processing scheduling, process scheduling. So the first, what is CPU scheduling or process scheduling? This scheduling will determine which process is going to do running by taking the CPU, right? It will determine, that scheduling will determine which process has to run. Means that running in the sense of that the process is acquiring the CPU for execution. So why this scheduling is so important? Means that it has a great impact on resource utilization, means, and also the performance of the system, because the system consists of many resources like CPU, memory, IPO, like different disks operation. So many of the resources are involved. So if you do perfectly the scheduling, so we can utilize the resources in a more effective way, right? That's the reason the scheduling is so important. So this diagram also discussed in the previous session. Now let us see very briefly how actually the process scheduling is represented in a queue. So in last session, we already talked about of the life cycle of a process and various process states, right? So here in CPU scheduling, let us briefly discuss about once again. Here, this figure is represent a queuing representation of the process scheduling. Here, whatever process is ready for execution, that process will be sitting ready queue. Here, if you observe here, this is a rectangular box. All in this entire of the figure, rectangular boxes represents queues. Different kinds of the queues we have already discussed. What are different kinds of the queues we have already discussed? Job queue, device queue, and ready queue, right? So these are the different queues we will use while in the scheduling. So once the process is ready for execution, that process will keep in the ready queue, right? Here, what other more queue you have seen? That the device queue, IPO queue, right? So here the circular, these are the circulars are represent the different resources which can serve to the queue. These are the different resources which can serve to the queues. And here these arrows are represent the flow of the execution of the process. While in the flow of execution of a process, different events are going to be happen, right? So this actually, when a process, if you observe the process state diagram, so ready and running, once IBO request is happen, then where it will go? It will go into the waiting state. Then once it is completing, IBO completion, then it will go back to the ready state, right? So these are the different states. You may already have seen that in the process state diagram explanation, right? So here the scheduler or dispatcher will take the decision which process has to take out from the ready queue and assigns the CPU to particular process. So that means that this is a scheduling. The decision of which process are given access to resources from moment to moment, that is meant by scheduling, right? So how we have to evaluate, because we are slowly going to the different kinds of the scheduling algorithms. So before enter into the scheduling algorithm, how we have to evaluate the performance of the scheduling algorithms? What are the parameters we are going to consider? So let us see the first parameter, CPU utilization. So everybody's intention is we have to keep the resource very effectively, has to use, keep the CPU as busy as possible, right? So that parameter has to be fulfilled. Now the next parameters, while doing the performance of scheduling algorithms, we will use the word throughput. Throughput is in the sense of that how many number of processes are completed their execution per unit time. How many number of processes, means like 10 processes are completed per 1 second or per 10 seconds. How many processes are completed their execution per unit time. That is nothing but throughput. So this is actually throughout entire of the operating system we will use while calculating the performance of the system. We will use this terminology. Please be remember. Throughput is nothing but the number of processes that complete their execution per unit time. So the next parameter is turnaround time. What do you mean by turnaround time? So in your examination, the questions will come, calculate average turnaround time, like that. What do you mean by turnaround time? Means that the difference between of process submission and completion of a execution. So it means the time from submission to completion of a execution. That is nothing but turnaround time, right? So the difference between of time submission and completion of a process is nothing but turnaround time. So what do you mean by the next parameter? Waiting time. Waiting time. So waiting time is in the sense of that the amount of time spent ready to run but not running. The amount of time spent ready to, because you have already seen, right, in ready queue. So the process, how much time is sitting in the ready queue to acquire the CPU. That time is nothing but waiting time, right? So or the amount of time a process have been waiting in the ready queue, right? That is nothing but waiting time. So the next, response time. the time between submission of request and first response to that request. First response means that CPU is assigned to the particular requested process. That is nothing but response time. Right? I am requesting, once you responded, the difference between of that time is nothing but the response time. So another parameter is scheduler efficiency. This scheduler, usually if you observe in the previous place also, this is scheduler, right? Scheduler will be placed between of ready to running. Scheduler will take the decision, right? So it means that it doesn't do effective work, very useful work, but it will be very key person to decide which process has to run, right? So we have to make the scheduler very efficient. We have to take the scheduler very efficient so that only the performance of the system will be improved. So these are the, once again, the parameters. What are the parameters? CPU utilization, throughput, turnaround time, waiting time, response time, scheduler efficiency. These are the different parameters we will consider while evaluating the any scheduling algorithms, right? So here, what is our intention? What is important in a scheduling algorithm? So before we have seen that, what do you mean by that parameters, right? Now, how actually it is very important in scheduling algorithms means that always the intention, if you are consider a very best scheduling algorithm, it means that it has to minimize the response time and maximize the throughput and fairness. These three has to maintained. So to minimize the response time means that the time to echo keystroke in editor. Suppose if I press any key in my keyboard, so how fast actually that letter is displayed, how fast actually I am getting the response, what the user sees. So suppose I have written a program and how fast actually I compiled and getting the response back. That is nothing but response time. So the maximized throughput means that the number of jobs has to executed per second has to be maximized. The throughput is related to the response time but not identical. So it means minimize the response time means that, okay, in a time sharing system we are trying to minimize the response time. With that, if you increase the context time, it doesn't mean that you are efficiently use the resource, right? So here, minimize the response time will lead to the more context switching. Context switching means the CPU will switch from one process to another process. So at the time of context switching, what we have to do? We have to save the state of a process. Right? Again, once that process is coming, we have to restore the process state. So then if you maximize only throughput, right? So minimize the overhead. So maximize the throughput means that you have to minimize the overhead as well as efficient use of the resources. If you perform these two, then only we able to achieve the throughput can be maximized. So the fairness means that you have to, some methodology, some way you have to share the CPU in equitable way. So it does not minimize the average response time. The fairness property means that share the CPU among users in some equitable way. It's not just minimize the average response time, right? So let us see the first scheduling algorithm, first come, first serve scheduling algorithm, right? So it is a first very simplest scheduling algorithm. So what is the main feature? It is very simple to simplest scheduling algorithm, very simple to implement. Here the name itself has given the meaning first come first served. In all real-time applications, we will see this kind of the scenario. Suppose when you have seen, can you able to give some examples of real-time examples where we will see that first come first served? So if you go to the railway station, if you go to the cinema ticket counter and different places, whoever is, what do you mean by first come? Means that the process that requests the CPU will get the CPU first, will allocate the CPU first, right? That only if you observe the real-time example. So here, see, this is a counter, ticket counter. This is ticket counter. So here the people are standing in front of the queue. So once actually she is acquiring the ticket, then only she able to move out from the queue. Whoever is first come, that person will start asking the request, right? So then she acquired the ticket, then she will move out from the queue. So this is actually real-time example. The implementation of the FCFS policy will be managed with a FIFO queue. You may have already seen in a data structure, stacks and queues. The queue, if you observe the queue, what is a queue will follow? Queue will follow FIFO kind of the policy. What do you mean by FIFO? FIFO means that first in, first out. First in, first out. First in, first out. Means that in any queue, it will follow the first in, first out policy. So here, the first we will consider, and if you observe that queue data structure, the first, the insertions will be happen at tile place, deletions will be happen at head end. So this side is head and this side is tail. Whoever is a person or element is going to come, it will add end of the queue, right? So the elements or the person will be removed at the head portion, right? So that is actually this FCFS also is going to be implemented in a queue data structure with help of FIFO queue, easily managed with the FIFO queue. So suppose while in the queue, two elements are having the same time requested. So that time, if tie happens, so then smaller process ID is going to be executed first. Smaller process ID means that, see, suppose if P1 and P2, because we already seen at the time of process introduction. So each and every process is associated with the some process ID. It is represented in the PCB, process control block. Each and every process is represented in PCB, process control block. Process control block is having of different elements are associated for the process. So in that, process ID will be assigned to the each and every process. See, first P1, P2. The smallest process ID means that, see, who will get, suppose if P1 and P2 is requesting for the same time, it is coming. Then, if tie happens, that smallest process ID will get first. Means that P1 will get first CPU. P1 will get allocation of CPU. Are you understand? So, now, here, when process enters the ready queue, its PCB is linked with the tile of the queue. When, okay, the process is acquired the CPU and it completed execution, then it is assigned to the process at the beginning of the queue. When the CPU becomes free, it should be assigned to the process at the beginning of the queue and the trending process will be removed from the queue. This is all about of the first come, first serve. What is the basic principle of first come, first serve means that the process that requests the CPU will allocate the CPU first. Right? That is a basic principle of this scheduling algorithm. So now after this we are going to see some examples to calculate the different times, different timings. So before enter into the solve of those FCFS that scheduling problems, so we will see one by one what are the different terminology it will come. These are the different terminologies is going to be come into the picture. The various times related to the process. We already have seen in the previous also the different parameters associated with the scheduling. So the first one is arrival time, waiting time, response time, burst time, completion time, turnaround time. So while solving any of the scheduling problem, these are the different times parameters we will use. So arrival time. Arrival time is the time at which process enters into the ready queue. Waiting time. Waiting time is the amount of time a process waiting in the ready queue. Waiting in the ready queue. This is actually we will use while calculating the waiting time, average waiting time for different process, for a set of processes. So that is waiting time equal to turnaround time minus burst time. Later we will see what do you mean by turnaround time and burst time also. So the response time is nothing but the amount of time after which the process gets a CPU first time after entering the ready queue. Very briefly, response time is nothing but time at which process first gets the CPU minus arrival time. Right? So the burst time is nothing but we already discussed execution time. Another word for burst time is execution time or running time. The amount of time a process required for executing on CPU. For executing on CPU. That is nothing but burst time. So is burst time can we know very early? Initial, before start of that? No. It can be only know after the process is complete the execution. Right? The burst time. So the completion time or another word we will use it as turnaround time or another word is exit time. Right? The completion time is a point of time at which process completes its execution on the CPU and take exit from the system. It is also called exit time. So the another time, very crucial one, very important one, turnaround time. The turnaround time means that the difference between of time submission and time completion is nothing but turnaround time. Right? Turnaround time is the total amount of time spent by a process in a system when it is arrived. The difference between when actually process is arrived and complete the execution. That differential time is nothing but turnaround time. Right? This is the formula. We will use it to calculate turnaround time. Turnaround time equal to burst time plus waiting time or turnaround time equal to completion time minus arrival time. So the all above definitions we have considered the process doesn't require an IBO operations. The before all the definition formulas we have calculated by considering it doesn't require an IBO operation and process is present in the system and waiting for the CPU to be in the ready state, for the CPU in the ready state, or it will be executed on the CPU. So now let us see the first problem. applying the first come, first serve scheduling algorithm. So let us take one first example. We have the set of 3 processes P1, P2, P3 with the following burst times: 24 milliseconds, 3 milliseconds, and P3 burst time is 3 milliseconds. And all this set of processes are arrived at time 0. Now, we will see that how we have to find the solution for this and what is the average waiting time and average completion time, right? So, if the process are arrive in the order of P1, P2, P3, right? What is the burst times actually for P1, P2, P3? 24 milliseconds. 3 milliseconds, P2 requires 3 milliseconds. P3 requires 3 milliseconds. To solve this problem, we will use a Gantt chart. Gantt chart is nothing but the pictorial representation of the process, arrival and completion. That we call it as Gantt chart. We will use that Gantt chart and calculate average waiting time and average completion time. Let us see. The P1 is coming and requested for CPU. So, no other process. The first come first serve basis, what the principle it is saying. Whoever first comes, P1 is coming first, right? P1 acquired, or for P1, CPU is allocated. So, the waiting time for the P1, what is the waiting time for the P1? Means that it is not waited anymore, right? In the ready queue. It is coming and requested for CPU, it is allocated. So, it means 0. P1 waiting time is 0. How much time actually the P1 is executing? P1 is execution time 24 milliseconds. So, till 24 milliseconds, the CPU is allocated to P1 process. So, if you may observe that the first important point is the FCFS is non-preemptive scheduling algorithm. Non-preemptive scheduling algorithm. In last session, we have discussed what do you mean by preemptive and non-preemptive scheduling. Once again, non-preemptive scheduling algorithm means that we are not able to take the forcibly CPU away from the process, right? That is meaning of non-preemptive. Preemptive means that forcibly we are allowed to take because some interrupt happen, some high priority process comes. Then actually we can allow to take away the CPU from the process. That is preemptive scheduling. So non-preemptive means that we are not supposed to take CPU from the process till the completion of the execution, or P1 voluntary has to given away, right? These two scenarios only actually is considered as a non-preemptive scheduling algorithm. So the FCFS means that whoever first and requested for CPU, it will be acquired and it will complete the execution. So here P2 arrive at time 0 and what is the burst time? 3 milliseconds. So till 24 milliseconds P1 is executed and then P2. So 24 plus 3, 27. 27 seconds, 27 milliseconds, P2 has completed execution. What is the waiting time of the P2? P2 is waited till 24 milliseconds till the completion of the P1, right? So the waiting time of P2 is 24 milliseconds. So like this, the waiting time of the P3, 27. Right? So till the 27 milliseconds, P3 is not acquired the CPU for execution. So what is the burst time of the P3? 3 milliseconds. 27 plus 3, 30. Right? So P3 able to finish the execution at 30 milliseconds. Right? So the waiting time is, for P1 is 0, for P2 is 24, for P3 is 27. And the completion time, execution completed. P1 is completed at 24 milliseconds, P2 completed at 27 milliseconds, P3 is completed at 30 milliseconds. So I hope everybody know that how to calculate average waiting times, right? Waiting time means that the summation of the all three process divided by number of processes in a system. Number of processes, the set. So here the average waiting time, the calculation of average waiting time, 0 plus 24 plus 27 divided by 3. So it is going to be 17 milliseconds. 17 milliseconds. Right? The average waiting time is 17 milliseconds if the process are arrived in the order of P1 and P2 and P3. So now let us calculate average completion time, turnaround time. So here we already know the values of for completion time of the P1, P2, P3, 24 plus 27 plus 30. 24 plus 27 plus 30 divided by 3 equal to 27 milliseconds. The average turnaround time of processes coming in the order P1, P2, P3 equal to 27 milliseconds. Now let us see the another parameter, throughput of a system. Throughput of the system means that the burst time of the processes, 24 plus 3 plus 3. So 30 divided by 3 equal to 10 milliseconds. That is the throughput of the system. Now let me see the if the processes are coming in the order of P1, P2, P3. Now what values we are getting? Average waiting time, or sometimes you people will write that AWT, average waiting time, ATAT, average turnaround time, right? So in this first case, P1, P2, P3 order 17 milliseconds and 27 milliseconds respectively. Now let us see, suppose if I change the order of the processes, you have to observe how actually, because P1 is having a longest burst time, P2 and P3 are having the shortest burst times, right? Suppose if I change the order and coming the process P2, P3, P1 order, let us see how actually this average waiting time and turnaround time will be vary. So if you observe that, now see P2 is coming first, P2 burst time is 3, the waiting time of the P2 is 0 because whenever it is coming, it is acquired the CPU, right? The burst time of the P2 is 3 units actually, the P2 is acquiring the CPU, right? 0 plus 3. The P2 has finished the execution. Now who is in that ready queue? P3. P3 is, the waiting time of the P3 is 3 milliseconds, because here we have considered all the process are arrived at time 0 milliseconds. Arrived at time 0 milliseconds. Now what is the waiting time for the P3? P3 waiting time is 3 milliseconds. It is waited in the ready queue, right? And the burst time of the execution time, how much time it requires? The CPU, it requires the CPU 3 milliseconds. So 3 plus 3, 6. So P3 has used the CPU 3 milliseconds. So 3 plus 3, 6. Till 6 milliseconds actually P2 and P3 has finished their execution. Now, what is the waiting time of the P1? So, P1 waiting time 6 milliseconds. P1 is waited and then acquired, allocated the CPU to the P1. So, what is the burst time for the P1? 24. 6 plus 24, 30. So, 24 milliseconds. P1 is using the CPU for completing the execution. How much time it is waited? 6 milliseconds it is waited in a ready queue. Right? So, let us see the values. So, P1 equal to 6 milliseconds. P2 equal to 0 milliseconds. P3 equal to 3 milliseconds. Right? The average waiting time means that 6 plus 0 plus 3 divided by 3. So, it means how much actually you got it? 3. So, in case 1, if the process arrive in the order P1, P2, P3, P1, P2, P3, what is the average waiting time you are getting? 17 milliseconds. Now, if they are executed in this order, how much actually, what is average waiting time? So, we are getting 3 milliseconds. So, it means that we are able to improve the performance or not. We are able to improve the performance in case 2. Right? So, what is actually, let us see the average turnaround time also. Average completion time. So, here P1 completed at what time? 30 milliseconds. P2 completed execution at 3 milliseconds. P3 completed execution at 6 milliseconds. Right? So, the average turnaround time or completion time equal to 30 plus 3 plus 6 divided by 3, because 3 processes are in the system. So, that equal to 13. In case 1, we are getting average turnaround time is 27 milliseconds. Now, in this case 2, P2, P3, P1, if process arrive in this order, 13 milliseconds. So, we have a great difference, right? So, the case 1 is better or case 2 is better? Case 2 is better than the previous case 1. So, this effect, what is your observation with the case 1 and case 2? Means that if you observe the problem, here see P2 and P3 are having the shortest burst time, P1 is having longest burst time, long time wants to use the CPU. So, it means that shortest power in the first case, the shortest power processes are waiting very long time in a ready queue, right, to acquire the CPU. That effect we call it as convoy effect. Convoy effect. What do you mean by convoy effect? So, the processes with higher burst time, in before example, who is having higher burst time? P1 is having higher burst time. If it arrives first, case 1, P1 is coming first, right? Before the process with smallest burst time, then smaller process have to wait for a long time, for longer process to release the CPU. That means that this is a very much drawback or disadvantage with the FCFS scheduling algorithm. That we call it as convoy effect. So, once again, we will see in the pictorial representation or pictorial way. See, longer job is taking the CPU first. This is engine, CPU. So, these shorter jobs are waiting long time. This we call it as convoy effect. With respect of parameter, if we observe that, the second case is a good, better performance, right? But here if that process, because due to of the FCFS policy, if the P1 or process is having longest burst time, and avail the CPU, the shorter jobs has to wait long in the ready queue. That effect we call it as convoy effect. So this is one example. So here in this example, we are considering all processes are arrived at time 0. Now let us see the another example. So here we have taken a set of 5 processes whose arrival time and burst times, the arrival times are different. Burst time are different. Right? So the question will be like, if the CPU scheduling policy is FCFS, then calculate the average waiting time and average turnaround time. What is the first step to solve this problem? What we have to do? We have to draw the Gantt chart. Draw the Gantt chart. Let us see. So here, this is a Gantt chart. So if you observe in arrival time, which process is arrived at time 0? P3. So after that, P1 is coming. After that, P5 is coming. After that, P2 is coming. Right? Arrival times. Based on that, now who are in the ready queue? At time 0, in queue, who are there? P3. At time 0, P3 is there. Right? Now, what is the P3 burst time? Execution time? P3 is coming and it acquires the CPU. Right? So, how much time? 2 milliseconds. Right? 2 milliseconds. P3 is executed. P3 is arrived at 0 and acquired the CPU for 2 milliseconds and executed. Now, 2 to 3. So, because here, is any other process are arrived at time 2? No. So, till at time 3, no process in the ready queue. Means that here, that time CPU is idle. Right? After that, who is coming? Who is coming? After that, this process 1. Arrival time is 3. What is the burst time of this process 1? 4 units. So 3 plus 4, 7. So P1 is acquired the CPU and executed. Right? 7. So after that, who is arrived? P3. Sorry, P2. P5. P5 is arrived. P5 is arrived. So what is the burst time of the P5? 3 units. So after that, P5. Right? At P5 is coming and then now let us see. P2 and P4 having the same time it is arrived. What is actually I have informed? If tie happen, the smallest burst time, the smallest process ID is going to acquire the CPU. So P2 and P4. So which one will acquire the CPU? P2 will acquire the CPU. So P2 is acquiring the CPU. Their burst time is, let me draw, otherwise P2 is completed at 13. P1, P2, P3, P4, P5. So 80. 35054, 35054, burst time 43213, 43213. Right? Now the entire data is with us. So now it is very clear P2 burst time 3. So 10 plus 3, 13. So P2 completed execution. Then who are left in the ready queue? P4. What is the burst time for P4? 1. 13 plus 1, 14. Right? So P4 completed execution. All the process in the ready queue has completed the execution. And this is. Now let us calculate the waiting time and turnaround time. Right? So waiting time. Let us see that for P1 how much time actually. So here while calculating waiting time. So P1 is arrived at 3. P1 is arrived at 3 milliseconds. And P1 is acquired the CPU. P1 is acquired the CPU at 3. So here waiting time is 3 minus 3, 0. So the waiting time equal turnaround time minus burst time. Time equal to turnaround time minus burst time. This is a formula have used. So let us see the P1 completion time. What is P1 completion time? 7. P2 completion time 13. P3 completion time 2. P4 completion time 14. P5 completion time 10. P5 completion time 10. Now while what is the turnaround time? We have used turnaround time equal to completion time minus arrival time. Turnaround time equal to completion time minus arrival time. This is a formula. Now turnaround time. While calculating turnaround time, 7 minus 3. Completion time is 7 minus 3 equal to 4. Right? Is it turnaround time for the P1? 7 minus the time submission and time completion. The difference between of time submission and time completion is nothing but turnaround time. So the formula we will use to calculate turnaround time equal to completion time minus arrival time. Right? So here completion time is 7 minus 3, 4. So for P2, what is completion time? 13. 13 minus 5 equal to 8. So here for P3, the completion time is 2. Arrival time is 0. 2 minus 0, 2. P4, completion time is 14. 14 minus 5 equal to 9. For P5, 10 minus 4 equal to 6. Right? This is now actually we have all the turnaround time for the P1, P2, P3, P4, P5 is 4, 8, 2, 9, 6 respectively. Right? Now let us see the calculation of the waiting time. The formula for waiting time is turnaround time minus burst time. So turnaround time what is actually 4. 4 minus 4, 0. So for P1, if you observe that the P1 is not weighted. Right? Even theoretically also P1 is not weighted. Whenever P1 is coming, it is getting the CPU. So 0. So now the turnaround time 8 minus 3 equal to 5. Turnaround time minus burst time. So another is for P3, 2 is the turnaround time. 2 minus 2, 0. So P4, 9 minus 1 equal to 8. So for P5, the turnaround time is 6. Burst time is 3. 6 minus 3 equal to 3. Right? So now we will calculate average waiting time. The turnaround time equal to completion time minus arrival time waiting time equal turnaround time minus burst time. Now we will calculate average turnaround time. So 4 plus 8 plus 2 plus 9 plus 6 divided by 5. Because the number of processes in the system is 5. That equal to 29 by 5 equal to 5.8 milliseconds. The next, the average waiting time 0 plus 5 plus 0 plus 8 plus 3 divided by 5. That equal to 16. 16 divided by 5 equal to 3.2 milliseconds. Right? This is what actually the calculations of scheduling algorithm. So now let us take another kind of scenario of example FCFS. If the problem comes like this, how we have to calculate? How we have to calculate the efficiency of the scheduling algorithm. So let us see. The third example. Consider the set of 6 processes whose arrival time and burst times are given in a tabular form. So 0, 1, 2, 3, 4, 5 is the arrival time of the P1, P2, P3, P4, P5, P6 and burst times are 3, 2, 1, 4, 5, 2. If the CPU scheduling policy is FCFS and there is a 1 unit of overhead. 1 unit of overhead means that the decision time, the decision overhead, right? So in scheduling the process, find the efficiency of the algorithm. Suppose if such a kind of problem comes, how to calculate? Here what they have mentioned, how much overhead it is there? 1 unit overhead is there. That is scheduling decision. Let us see. To solve that problem, we have to draw the Gantt chart. The first 0 to 1 unit, because they have mentioned scheduling decision overhead is 1 unit. So 0 to 1, it will spend the delta amount of that. That delta is 1 unit that is given in the problem, right? That is given already in the problem. So for my simplicity, I have again bring it out that table in this slide also. So now come to the P1. P1 is arrived at 0. But 1 unit scheduling decision is happened. Then it acquires. The burst time is 3. So 1 plus 3. P1 is executed CPU and finished the execution at 4 milliseconds. After 4, it is completed. P1 is completed execution. Right? Now come to the P2. P2, while taking the, who has to take that 1 unit, delta unit, 4 to 5 has to be taken decision overhead. So then P2 is coming at 1, arrival time at 1, but it acquired the CPU at 5. So it means that 4 units actually it is waiting in the ready queue. So P2 is, burst time is 2. P2 able to 5 plus 2, 7. P2 completed the execution at 7. P2 completed execution at 7. Now P3, 1 unit of the time, decision overhead, scheduling decision overhead. Then P3 arrived at 2 and the burst time is 8 plus 2. Sorry, P3, 8 plus 1, 9. So P3 completed execution. Now 1 unit, 9 to 10, decision overhead. Then 10 to, like this actually all the process finished the execution. Now this delta is 1 unit context switching overhead or scheduling decision overhead. So now useless time, see, by wasted time. How much time actually it is wasted in entire of this scheduling? 6 units, right? Because 6 processes are there. 6 units it is wasted, right? 6 unit. Useless time is 6 units. Total time is, how much total time actually when actually all the process able to complete the execution? 23. At 23 units, actually all the 6 processes are completed the execution. Now useful time is 23 minus 6 equal to 17 units. 17 units actually the CPU is executed by the all processes are executed in and using the CPU time in 17 milliseconds. So now calculating the eta, efficiency of the scheduling policy. So useful time by total time, right? So useful time how much? 17 by total time 23. This is the efficiency of the scheduling algorithm, 0.7391. Okay. So with this, we have covered all the different possible cases with respect of FCFS scheduling algorithm. Now let us see the what are the different advantages and disadvantages with this scheduling algorithm FCFS. So the first, as I have mentioned, it is a very simple algorithm, very simple CPU scheduling algorithm. So the another very advantage is very easy to implement. So here what data structure we have used? We have used the data structure is queue, right? So the first in first out policy. It is very easy to implement. So what are the disadvantages? We already have seen that convoy effect. That is a very much disadvantage, because we observed that case 1 and case 2. Case 2 is having a much better than the case 1, right? So the main disadvantages are, it is a non-preemptive scheduling algorithm. Any high interrupt and any high priority process also come, then the CPU can't able to give away to the other process. That is the first major drawback. And another drawback is the average waiting time is high. If you observe that in the first case 1. So the average waiting time is high, and short process that are the back of the queue have to wait for a long process in front to finish. So that is nothing but convoy effect. That is a disadvantage of the FCFS scheduling. So if you observe with the examples, the performance of the algorithm is based on the order of the process which are arrived, right? So the performance is highly dependent on the order in which jobs or process are arrived, right, in a system. So not ideal technique for time sharing system. This is the disadvantage of the FCFS policy. These are the references. The major book is a Galvin book and Tannenbaum book and Geeks Gate Vidyalaya tutorial point. These are the books actually we have referred to make this presentation. So thank you.
Like, share and subscribe. Hit the bell icon for more updates.